All right, thanks so much, you guys. See, that was for you, Dad. Yeah, I need technical help, too. This has been great, really, seeing everybody show their support and say such nice things. I guess I've been seeing all the lessons people have learned from him, and that's how I'll be talking about, going about this talk, is I'm going to share chronologically a series of lessons that I've learned from my dad, Dick Karp. And I hope you guys learned something, too, from it. So I'll start off at the very beginning in 1988, and here we are on a nice day in Berkeley. And the very first lesson I learned from him was to take time to enjoy a nice day. So Shafi was saying that he was always really patient in terms of meeting with students and wondered whether that translated to his personal life, and I think it does. So it took some time for me to appreciate it, but he always likes going for long walks and people watching, and takes time out to have a sit-down lunch every single day, regardless of his schedule. And I think in this world, that's admirable to not be in a rush. And while he's relaxed and patient, he also gets a lot done. And I think he wanted to translate that to me, so he didn't waste any time, and he set me up with some of the world's best tutors. So here I am getting a lesson in zero-knowledge proofs from Manuel and Lenore Blum. And shortly after, they showed me the analysis of randomized quicksort with Don Knuth. So the lesson here is to, again, stealing from Shafi, to collaborate and learn from the people around you. But all that theory is well and good. He saw that computers were not going away, and so he wanted to quickly set me up with some more applied techniques. So here we are. We learned Leisure Suit Larry. We learned Kid Picks. But also, I learned UNIX at a very young age, even though we had MS-DOS and later Windows. And just a fun fact, as late as 2013, Dick was using the command line to check his university email and insisted that there was no other way to do it. So I'm not sure about that one. But I appreciate the early computer support. And here we are a couple years later. Honestly, I'm not sure what the lesson was here, but I think that went over my head. But there's more, and I think some more valuable ones. So I'm going to fast forward about 20 years now, and I'm in my first year of graduate school at Carnegie Mellon University in Pittsburgh. And at the time, my research interest was in approximation algorithms for combinatorial graph problems. And so the fifth lesson, in a slight turn of events, was the held Karp paper from 1970, the traveling salesman problem in minimum spanning trees. And I'm not the only person at this workshop to touch on that. I think this impacted a lot of people. But I want to quickly talk about a few things and how it remains relevant to us today. So first of all, in this paper, the probably most famous contribution for it is that they formulated a linear programming relaxation for the symmetric traveling salesman problem. And this is known as the subtour LP now. And this in the approximation algorithms literature remains very relevant as a starting point for all kinds of approximation algorithms for the traveling salesman problem. And, but at the time, this was an OR paper, and so a lot of it was about a heuristic they had that used a Lagrangian method to find a one tree with the same cost as the subtour LP. And I went back when preparing for this talk and looked at the original paper, something I think I'd seen the results summarized many times, but I hadn't actually read the original 1970 paper. And I saw that they are very proud to say they have a branch and bound procedure that uses these lower bounds to solve instances of up to 64 cities to complete optimality. And what's great about this is that these first two bullets really show techniques that inform and remain relevant today. But one thing that has dramatically changed is the computing power. And so I did a quick Google search, and I saw that as of 2007, there's the Concord Solver that can use these techniques as well as all kinds of fancy cutting planes and other things to solve traveling salesman instances optimally with up to 25,000 cities. So I hope that impresses you and that you see how your contributions are still informing us today. And the reason I was so interested in this is at the time I was working on approximation algorithms to the graphic TSP problem. So that problem is the traveling salesman problem on shortest path metrics of undirected, unweighted graphs. And I was specifically interested in approximating solutions to this problem in cubic bipartite graphs. So these are graphs of degree 3 and bipartite. And so this class of graphs allows us to leverage the structure to get improved approximation factors, but also keeps much of the complexity of the original problem. And it also is interesting because it ties into Barnetts Conjecture, a conjecture in structural graph theory that says that if it's true, every bipartite cubic polyhedron is Hamiltonian. And so I'll explain in a second after showing the result why this relates to that. So the main result is that given a cubic bipartite graph, there's a polynomial time algorithm that computes a solution with at most 9/7 and -2 edges. And this is joint work with my advisor, R. Ravi. And so the way we obtain this result is we want to find a cycle cover in the graph with relatively few cycles. So the general approach, if you're able to do that, is you find a cycle cover with k cycles in your graph. You compress each cycle into a single node and compute a spanning tree in this new compressed graph. And then you take your cycle cover and join it with 2 copies of the spanning tree to get a solution to the traveling salesman problem with n plus 2k minus 1 edges. And so our main result, while it can be viewed as an approximation algorithm, it's also a constructive proof of a structural result that any cubic bipartite graph has a cycle cover with at most n over 7 cycles. And so this is where it ties back into the Barnetts conjecture in the sense that that's saying that these graphs, or this more specific class of graphs, can be covered in a single cycle. And one way to make progress towards that is by showing that you can cover it with as few cycles as possible. And so it's an interesting secondary way to view this result. Now, more recently, my interest has shifted more towards operations research, and I've been working on methods and models for solving optimization problems related to omnichannel retailing. So this is a little foreign maybe to the crowd in this room, but what this really means is that retailers, like whether it's department stores or Target or Walmart, are selling their products through multiple channels. So that could mean they have physical locations and they also have an online website. And instead of maintaining completely separate warehouses to sell their online products, they instead can find savings by fulfilling online orders directly out of the retail stores. And so there are many benefits to this, but one of the challenges that comes with this is that there's the possibility to overcommit inventory, which leads to the failure of orders. So you can imagine that an item is listed in the inventory because it's at several retail locations. A customer orders that item online, and then the clerk goes to pick it up and put it in a box, but someone has purchased that item in the real physical store, or the item has been moved around or lost, and just in general, inventory in physical locations of brick and mortar stores is less reliable than the inventory in a dedicated warehouse. And so I'm looking to model and develop methods to solve optimization problems that work with the trade-off between filling as many of these orders as possible so as to generate revenue while limiting the costs associated with orders that fail. And so I thought I'd maybe finally was done learning lessons from my dad, but then in the process of working on one of these problems, I came across the Karp-Vazirani paper, an optimal algorithm for online bipartite matching. And this actually is probably, of all the things that he's done over the years, this one really stuck with me as a profound and interesting result. So I wanted to share it with you. I think probably half of the room knows it, but it's possible that some of you don't. So you have GUVE is a bipartite graph, and the setting is that the V nodes arrive in an online order while the U nodes are known. There are n of each. And when a V node arrives, it must be matched to an available U node upon arrival. And the goal, naturally, is to get as large a matching as possible. And so the naive algorithm here is just to match each node to a random available node. But what Dick and his collaborators did is they realized that that's not going to work out very well. What you need to do is you need to assign all of the U vertices a random ordered ranking prior to the arrival of the V nodes. And doing all of this randomization in one step as a pre-process, and then matching each of the arriving nodes to the highest ranked neighbor as it arrives, gives you a dramatic improvement. So instead of getting, at worst, n over 2, you're able to get a matching of size n over 2 plus big O of log n, and an expectation. And I think this is a really interesting result, and I know that you're mostly interested in theory, but at the same time, you couldn't have predicted Google AdWords, and now this is a problem that all kinds of people care about in many different communities, and all of these results are based off of this paper, so that's really neat. And also, since I'm an OR guy, I liked seeing that in 2007 there's a Devner, Jane, and Kleinberg paper that does a primal dual analysis of this ranking algorithm. And so while I always thought that this result was really interesting, the analysis in the original paper was a little difficult to follow, at least for me, and it was not necessarily revealed too much of the intuition for what was going on in the algorithm. But then there's this really great, simple primal dual analysis that ties it into linear programming in a nice way, and also gives a lot of intuition into why this algorithm is so effective. And so I'd like to end by talking about an online problem that I was working on, which led me to familiarizing myself with this work. There are a bunch of different ways to formulate these retail optimization problems, but one way in particular is to use competitive analysis. So you say that that there are a set of S stores, and that you characterize each order that comes in by affiliating it with the closest store to where the customer that's ordering it is located. And then you have to decide when the order arrives, do you accept or reject this order? And then if you've accepted the order, you're committed to filling it and you receive a profit accordingly. But also, you must decide which store is going to fulfill it and pay a shipping cost from that corresponding to the distance between the two stores, and also pay a cost based off of the probability of that order failing. So to formulate that as a math problem, you say there's a shipping cost metric between the different stores. So shipping an order from store I to J has cost Sij. And if we accept X orders from store I, we receive a profit of XR, representing a fixed profit for each accepted order. But then we also must pay a cost, Fi of X, for these orders, which is a convex function reflecting that there's an increased marginal probability of failure for each additional order that is accepted by this location. And so the orders and decisions occur in an online stream, and so we want to use competitive analysis to work on this problem. And we quickly realized that this is very related to online matching or allocation problems, because you can think of a nice bipartite graph here, or well, there are many ways to think of it. And so I guess the sort of preliminary result here is that we can see through a reduction to a combinatorial auction setting that a simple greedy algorithm is half competitive here. So the way this reduction works is that you think of the orders are the items that are being auctioned, and the stores are the bidders. And then you can think of X as some set of orders, and you can define for each store a valuation function over these sets, which corresponds to the profit that's generated by filling these orders out of that store. And there's a result from 2001 that says that a greedy algorithm, so where you, as the orders come in, you give it to the store, to the bidder who gains the most marginal utility from taking this, is half competitive. And so what's, I guess, unfortunate for us is that there's also a result that says that no online algorithm, randomized or deterministic, is going to do better than one half competitive for these combinatorial auctions with submodular valuation functions, unless NP is equal to RP. Now, as Sanjeev Arora pointed out, this is for over the class of all submodular functions, and we're working to show that to translate the proof of this hardness over to within our specific class of valuation functions, but I can't say with certainty that that's the case. But one thing that I'm looking at going forward is the impact of recourse on these algorithms. So in the real setting where we formulated this model, as the orders arrive, you need to make an immediate decision whether the retailer accepts or rejects the order, but you may have time before you have to decide how the order is allocated. And so one avenue that I'm pursuing right now is to see if a better than one-half competitive algorithm can be formulated by allowing recourse in this sense. Then I'm going to quickly just mention some of the other topics within this area of omnichannel optimization that I find very interesting and am currently pursuing results on. So one of them is trying to formulate stochastic optimization problems. So instead of this online setting where you have an adversary feeding you the orders, you can say that you know certain prior demand probability distributions over the demands and try and solve various sort of news vendor-like optimization problems in this setting. And I've had some success with my advisors on solving these formulations, but this is still a work in progress. And then a nice extension of this that translates back a little bit into the theory community is understanding learning rates from observed data. So in reality, it's unlikely to be known what these probability distributions of demand for items are, as well as the probability distributions for order failures. And so one interesting set of problems is where you have observed data of historical demands for items and the success and failure of these orders that were accepted, and using that to learn these rates on the fly and make optimal or near optimal decisions. And there's been some work in the area of sample average approximation for trying to use this historical demand and prove guarantees of if you want a solution that is within a certain factor of epsilon close to optimal with a certain probability, upper bound on the number of samples needed. And I have some preliminary results that I'm developing in this area. And lastly, one thing that's very interesting is we've been working with several real retailers who have offered us their data to help them do more empirical work on this topic. And one of the issues that occurs is that they open and close these sales channels, and as a consequence, there's censoring of the data, because you observe the demand when the sales channels are open, but as soon as the channels get closed, you're no longer able to observe this data. And so you need to apply advanced techniques to be able to understand the impact of this censoring and how the policy that you're running over time is affecting the data that you're collecting. And there's various issues associated with this. So hopefully by CarpFest 90, I'll have some of these problems worked out as well as others, and it'll be exciting to share them with you. So thank you so much for the lessons, Dad. I hope you're enjoying the day and continue to enjoy it. So happy birthday.
Any questions?
So once you have actually an opportunity to see the real data, like how well the online algorithms did work on them?
So the data we were working with, we were actually doing a single store problem. So we were trying to use features of the items to predict the cancellation rates and do a machine learning based approach on it. Yeah, so that was sort of a different problem we were working on.
Okay, thank you again.
Thank you.